The stars of our universe, be it big or small, all stem from one singular source, nebulae. A nebula is a collection of hydrogen-helium gas, 97% hydrogen and 3% helium, with a diameter of about 0.143 light years across. The reason that nebulae are able to form, and therefore stars, is due to the extreme coldness of space. With temperatures at almost absolute zero, particles are moving extremely slow. The collision and sticking of cooled microscopic dust and ice particles electrostatically, due to extreme temperatures forming superheated balls of gas and flame which gravitationally accrete more smart particles, is the process in which stars are formed. This process is called accretion and takes around 10 million years to complete. However, a star is not fully formed after this process is finished. It must go through another stage in its life cycle. After the collection of hydrogen and helium has gathered to a mass of approximately 2 × 10 to 28 kilograms, it becomes a protostar. A protostar is an early stage in the evolution of a star, after the beginning of the collapse of the gas cloud from which it is formed, but before sufficient contraction has occurred to permit initiation of nuclear reactions at its core. The word proto means earliest form of. Therefore, a protostar is the earliest form of a star, or it can be also thought of as an infant star. Its temperature compared to a fully formed star is minuscule, only 2,000 to 3,000 degrees Kelvin, and is red in color. Any form of light emitted from a protostar is part of the spectral emission of early fusion of hydrogen gas molecules. This stage of a star's life is very short. It only lasts for about 100,000 years. After this is when a star is said to spend most of its stellar life. The life cycle of a star cannot be truly understood until it has reached its main sequence. The main sequence is the stage where the star spends most of its time. In this stage, the star consumes hydrogen for fuel to burn and survive. The typical star spends billions of years in this stage. However, for a star with a mass of 300 solar masses, a blue supergiant, whose radius is 74 times greater than that of our Sun, whose luminosity is a million times greater, and whose surface temperature is 40,000 degrees Kelvin, this time is extremely short. Some say that such stars live fast and die young. They are very much correct. Stars as massive, or as close to as massive as a hypothetical 300 solar mass star, will burn through their hydrogen supply and begin to look for other sources of fuel as they begin to form helium, carbon, oxygen, and iron through nuclear fusion. Once the fusion has occurred, the blue supergiant's outer layer of gases will expand to form a red supergiant. A red supergiant will swell to the size of 1,000 times that of our Sun, and have surface temperatures of only 5,000 degrees Kelvin or higher. The red supergiant will continue to shed mass and become a Wolf-Rayet star. Such stars are extremely hot, with surface temperatures ranging from 30,000 degrees Kelvin to 200,000 degrees Kelvin, and have luminosities several millions of that of our Sun. Wolf-Rayet stars are evolved massive stars that lose much of their mass through stellar wind, a flow of neutral or charged gas ejected from the upper atmosphere of a star. From this stage, the star will continue to eject mass until death. However, there is another possible outcome for a red supergiant. It can become a hypergiant. A hypergiant is a star that is so large that it has the ability to reach a radius greater than 1,500 solar radii. It is not clear what type of hypergiant this hypothetical 300 solar mass star will become, but through recent observation, it can be inferred that a post-red supergiant that has already lost most of their atmospheres and hydrogen will become a yellow hypergiant, with their luminosity at around 500 to 750 times greater than that of our Sun. Blue supergiants can become much more luminous, reaching several billions times greater. Hypergiants are only created in the largest and densest areas of star formation, and because of their short lives, only a small number are known. despite their extreme luminosity that allows them to be identified even in neighboring galaxies. The main sequence of these types of supermassive stars will only last a few billion years, and will end with catastrophic proportions. After the yellow hypergiant has collapsed in on itself due to the force of gravity, the star will die with a supernova greater than that of any ever recorded. The explosion will rival that of even the brightest galaxies. It will destroy everything within millions of miles. This hypernova has two possible outcomes. It can either 1. Form a supermassive black hole with energy expelled through gamma ray bursts, or 2. The explosion will be so devastating that no remnant of a stellar explosion will be left behind.
In summary, a star with, or close to, 300 solar masses will be extremely luminous, extremely hot, and extremely large compared to solar standards. This is why these supermassive stars will be outliers in the HR diagram, sitting above the main sequence and the giants. They will be in the supergiant cluster of stars, and in rare cases, in the newly evolved hypergiant area. They can range from Class O to Class K. They are the alpha stars.